Today I would like to continue our discussion about the early moon. Last time we discussed how the moon likely formed in the aftermath of a giant impact and that it likely formed very hot. We think most of the moon may have been molten rock. This molten rock layer is called the Lunar Magma Ocean, and today we'll consider how it cooled over time. We celebrated the 50th anniversary of the Apollo 11 landing this past July, and another 50th anniversary is coming up. In January 2020, we will be celebrating the 50th anniversary of the Lunar Magma Ocean idea, which was initially proposed by two groups, their papers shown above, after they had analyzed anorthosite fragments in the Apollo 11 sample collection. Last time we saw the standard or canonical giant impact model. In this model, the early Earth is impacted by a Mars-sized object, often referred to as Theia. That giant impact produced a lot of hot debris and put it into orbit around the Earth. Some of that debris then accreted to form the moon. Notice again that the figure on the right shows an edge-on view of the disk with the colors indicating the temperatures in Kelvin. Not only did the moon form out of material that was very hot, in the range of thousands of Kelvin, but the moon was additionally heated in the formation process itself, as we will see in a moment. Before that, I'd like to make a brief statement about math. Since this course is intended for a general audience, I'm not going to talk about a lot of math, but I'll occasionally show an equation. I know some folks don't like math, and many may be turned away from science because of it. I mainly blame this on the nonsense that people are told when they are young, that they are, quote, not a math person, or, quote, not good at math. My philosophy about things like this is similar to the motto in the Pixar movie Ratatouille, anyone can cook. I think anyone can do math, but you may not want to, and that's okay. Math is a language that helps us describe things in a very compact way. You can write the equation F equals ma completely in English or any other language, but it's likely to be a paragraph of text instead of 3 variables and 1 symbol. So if I show you an equation and you don't understand it, it's okay. I'm happy to help. You can understand it. Much like learning a foreign language, it just takes practice. Okay, now let's look at an equation. This is the equation for the gravitational binding energy of an object. There are 2 ways to think of gravitational binding energy. One is to think about a planet. What if you wanted to completely break it apart? By that I mean you want to take small pieces of the planet and move them very large distances away from each other. Obviously, planets don't just break apart in this manner naturally. You would need to add a considerable amount of energy for a planet to break apart in this way. The energy required to do this is the gravitational binding energy, U. It depends on the universal gravitational constant, G, the mass of the planet, M, and the radius of the planet, R. Note that technically this is the minimum energy required since you'll likely need to add additional energy to break the bonds between solid objects. The other way of thinking about the gravitational binding energy is to think about the opposite process, the formation of a planet. Imagine that small pieces of material are very far away and slowly they collapse due to gravity to form a planet. In this case, gravity is doing the work. But all the small pieces of material had some gravitational potential energy when they were far away. Energy doesn't just disappear, so all that energy needs to go somewhere. That energy, which is the gravitational binding energy, is converted to heat. Now there's a subtle point about the heating process. Yes, there is a large quantity of energy that is released when a planet forms, but whether or not that melts the planet has to do with the speed at which the planet forms. If the planet forms rather slowly, say over 1 billion years, then there would be plenty of time for that energy to be dissipated away. However, if the planet forms very quickly, then there isn't enough time for that energy to be dissipated. As such, that energy goes into melting the planet. So going back to the moon, here's another reason why the moon likely started in a molten state. Not only were the materials that made the moon starting off at thousands of Kelvin in temperature after the giant impact, but since the moon likely formed very quickly, that is to say in about 1 year, that gravitational energy would have gone into melting the moon. We saw last time that moon rocks seem to agree with this notion that the moon was molten in the past. We already saw this sample from Apollo 15, which is colloquially called the Genesis rock, since it was thought to be a piece of the original crust of the moon. This rock is unique in that it's basically made of one mineral, that is to say plagioclase. If you pick up a rock outside, that rock will likely be made of a number of minerals. Rocks like this one from Apollo 15 are called anorthositic rocks, and finding them on the moon led scientists this to propose that a large part of the moon was molten rock in the past. Here's another Anorthosite sample, but this time from Apollo 16. Notice how you can see the lighter colored Anorthosite once they cut open the rock. Anorthositic rocks like these likely formed from the solidification of the molten moon in the past. This is an overview of how the moon solidified over time. There are various estimates of the Lunar Magma Ocean, LMO, depth, but we can assume that it was about 1,000 kilometers deep. Note that the radius of the moon is about 1,737 kilometers. That means that the early moon largely consisted of the Lunar Magma Ocean. The Lunar Magma Ocean would have solidified in two stages. First, as it cooled, it would form minerals like olivine, which being more dense than the surrounding liquid would have fallen to the bottom. As such, the Lunar Magma Ocean would have solidified from the bottom up. Once about 80% by volume of the Lunar Magma Ocean had solidified, there was a change. The mineral plagioclase became stable and started to form anorthositic rocks made mostly of the mineral plagioclase. Anorthositic rocks that formed would have been less dense than the surrounding magma, and as such they would have floated to the surface. The rocks that floated to the surface would have formed the primordial crust of the moon. Fragments of that early crust were picked up by the Apollo astronauts and brought back to Earth. Note that the first stage, going from the initial Lunar Magma Ocean to the point when 80% of it was solidified, would have occurred rather quickly, in about 10,000 years. On the other hand, the second stage would have taken tens or even hundreds of millions of years. The difference is because the flotation crust acted as a thermal blanket and reduced the amount of heat through the surface. Besides Apollo samples, more recently spacecraft data have helped researchers identify areas of the moon where there are pure anorthosite, shown in white circles above. Note that the center of the map consists of the near side of the moon, the side we see from the Earth, and the left and the right sides of the map are showing the far side, the side we cannot see from the Earth. This particular map is plotting surface elevations along with locations where there are pure anorthosite material and locations where there are olivine-rich material. The distribution of these pure anorthosite locations across the lunar surface likely indicate that there was a global layer of anorthosite on the moon. Are there other pieces of evidence to support the idea that the early moon was mostly molten? Yes, the abundance or lack of the element europium is likely the result of the crystallization of the Lunar Magma Ocean. Europium is interesting because it is attracted to plagioclase. As such, when the lunar crust was forming, europium in the Lunar Magma Ocean went into the early lunar crust and was removed from the Lunar Magma Ocean. Notice in the figure above how the crust tends to have more europium as compared to creep, potassium, K, rare earth elements, REE, and phosphorus, P. Creep material is representative of the last magma of the Lunar Magma Ocean, so it makes sense that it has less europium because it has gone into the crust. Now, I want to briefly look at how we model the Lunar Magma Ocean in computers. To model the Lunar Magma Ocean, we first need to estimate what the chemical composition of it was after the moon formed. The simple explanation of how people have done this is that they estimated the chemical composition of the Lunar Magma Ocean by considering the chemical composition of the Earth's mantle and adjusting it from there. As you probably remember, the moon likely formed mostly from Earth's mantle material, so this is a reasonable way of doing this. Various groups have different estimates for the Lunar Magma Ocean's chemical composition. I've shown here 7 estimates from previous works. The next step in the modeling process is to figure out which minerals would crystallize out of the Lunar Magma Ocean. Let's say we chose chemical composition D. In that case, the first stacked graph on the right shows the expected sequence of minerals. This is based on numerous experiments that showed the types of minerals that crystallize out of different types of magma. Obviously, the minerals that form are derived from the molecules that are present in the Lunar Magma Ocean. From the bottom to the top, the graph shows that the mineral olivine would form first, followed by other minerals. Towards the later stages of crystallization, the low-density material plagioclase would form. Note that in the graph, plagioclase is shown as AN because it's a specific type of plagioclase called anorthite, not to be confused with anorthosite. While anorthite is the calcium-rich type of the mineral plagioclase, anorthosites are rocks mostly made of plagioclase. In summary, the minerals that crystallize out of the Lunar Magma Ocean are dependent on the initial composition of the Lunar Magma Ocean and the pressures and temperatures that are involved. If the Lunar Magma Ocean was much shallower than 1,000 kilometers, then even with the same initial chemical composition, we would expect a different sequence of minerals to form since the pressures involved in the cooling process would be different. The process of lunar magma ocean solidification involves many interacting factors. This is a sketch of the many of the things that should be considered. For example, we expect the lunar magma ocean to have been convecting and the surface to be radiating. However, we should consider if quenched crust formed on the surface. Formation of quenched crust would have placed a conductive lid that slowed the cooling process right from the start. Another important aspect is the detailed crystallization process. Additionally, impacts may have played a role. Impacts could have punctured holes in the flotation crust, increase the heat output, and thereby quicken the cooling of the moon. So far, no computer model incorporates all of these factors at the same time, but future works will consider how all of these factors interact to produce the solidified moon we see today. We saw this timeline of important early lunar events last time. The age of the solar system is estimated by the oldest calcium aluminum rich inclusion, CAI, shown by the dashed black line. The moon is thought to have formed between 52 to 152 million years after the beginning of the solar system. Thus, the earliest and latest moon formation times are shown in blue and orange lines respectively. One recent work used computer modeling to calculate that the lunar magma ocean took 30 million years to solidify, without the influence of any cooling or heating mechanisms such as impacts and tidal heating. I've added lighter colored rectangles next to the solid blue and orange lines to represent the time required for the moon to solidify. Now let's take a look at the ages of moon rocks. Particularly, let's consider radiometric ages of Pharoran Anorthosite or fan samples. I'm showing here the oldest and youngest Pharoran Anorthosite ages along with their respective error bars. There are many other age dates in between, but for this discussion it's useful to only look at the oldest and youngest dates. First, note that there are large error bars and that the oldest Pharoran Anorthosite sample seems to be as old as the solar system. That's unlikely. Also, notice that the time difference between the oldest and youngest ages is about 270 million years. If these are pieces of the original crust of the moon, then the difference in ages should indicate to us the solidification time of the lunar magma ocean. Recall that one calculated estimate for the lunar magma ocean solidification time is 30 million years. 30 million years is much shorter than 270 million years. So this could mean that the lunar magma ocean had an additional heat source to keep it hot. For example, tidal heating has been proposed as a mechanism for heating the lunar magma ocean. This is a possibility. However, how reliable are the ages of the Pharoran Anorthosites? Recently, Borg and others graded the ages of the various age estimates using 5 criteria. Only one Pharoran Anorthosite sample met all 5 of their criteria. I'm showing that sample's age here as the best fan age. I've also included the error bars, but the error bars are much smaller than the red square marker. The Borg paper also estimated the age of that incompatible element or creep layer. Note that is the German prefix for original. Notice that the best Pharoran Anorthosite age and the estimated age of the original creep layer basically overlap. That makes sense that an anorthosite that formed towards the end of the lunar magma ocean crystallization process would have the same age as the last bits of the lunar magma ocean. However, we don't really have a very reliable estimate for the age of the oldest anorthosites on the moon. Finding a very reliable age for the oldest anorthosite would help make the ages of the lunar crust samples consistent with the computer models of the lunar magma ocean. That would mean we have a more complete understanding of how the moon solidified than we do today. I now want to talk about a possible issue with the lunar magma ocean model. To do that, let's consider the different types of lunar anorthosites. We have already seen Pharoran anorthosites, or fans, which are rocks that are mostly made of one mineral, plagioclase. More specifically, Pharoran anorthosites are made of the calcium-rich variety of plagioclase. Recall that version of plagioclase is called anorthite, and it's shown above as AN. Another type of lunar anorthosite has a bit more variation in terms of the amount of anorthite in the rocks and has more magnesium than Pharoran anorthosites. That group of anorthosites is called the Mg suite for magnesium. There is also another group of anorthosites called the alkali suite, but we won't be discussing them today. When these different types of anorthosites were discovered in the Apollo sample collection, it was proposed that the Pharoran anorthosites were pieces of the original flotation crust of the moon, and the other anorthosites, like the Mg suite of rocks, were produced later in the moon's history. As such, when these samples' ages were measured, the expectation was that Pharoran anorthosites would be old and the Mg suite rocks would be younger. However, this isn't the case. This figure shows the ages of Mg sweet rock along with Pharoran anorthosites. Please note that in this figure, Pharoran anorthosites are referred to as FAS for Pharoran anorthosite sweet, but the more common acronym is FAN. The plot is a bit backwards since the beginning of the solar system is in the middle at about 4,567 million years ago, or equivalently 4.567 billion years ago. Then time progresses to your left. As you can see, there is significant overlap in the ages of Pharoran anorthosite and Mg sweet rocks. This issue has been recently raised and is part of ongoing research. While the lunar magma ocean is the standard idea of how the moon solidified over time, there are other ideas that have been proposed as well. One idea is serial magmatism. In this model, plagioclase-rich diapers, or plumes, rise much like the lunar magma ocean model, but they get lodged into already existing crust on the moon. One difference between the two models is that a plagioclase-rich crust should be global in the lunar magma ocean model, but in the serial magmatism model, it's more sporadic. Future work may be able to distinguish between these two models by understanding how widespread plagioclase material is throughout the lunar crust.